Welcome to the second part of these notes. It starts with the mean value theorem for integrals. And the mean value theorem states this, that if f is a continuous function on an interval ab, a closed interval, then at some point between a and b, the integral of f of x, so the area under the curve, is equal to the area of a certain rectangle that has that base, the interval itself, and a height f of c. So let's see on this graph what it looks like. I have a function f that is this curve here, and my area under the curve is equal to a certain rectangle. I tried to guess what this rectangle would be like. It's this rectangle here, which is higher here but lower here, and the area of this rectangle is equal to the area under the curve. And the mean values theorem states that this is always true and that we can find a point on the graph of f which has the appropriate height. The requirement that f is continuous is obvious. We need the function to be continuous to make sure that there is a point with the appropriate height. So I wrote it like that here. The area under the curve is equal to the area of a certain rectangle in the interval. Again, the mean value theorem doesn't tell us which rectangle, but it states that there is a rectangle that has this property. The average mean value of an integrable function, the average value, so the mean value of a function, is actually found directly by using this function. If you divide this equality by b minus a, you will find this. F of c, the average of f, is equal to 1 over b minus a, and you have to integrate the function from a to b. So let's have a look at an example here. Find the average value of this function f of x equals root 4 minus x squared. It's a semicircle, so it's quite interesting to wonder what is the average height. Here it's very low, here it's high. What is the average height of a semicircle of radius 2? So I'll just move down. If we look at this equality here, we just plug in the values. The upper limit is 2, the lower limit is negative 2, because we're integrating from negative 2 to 2, and then we have to integrate root 4 minus x squared. Now, we know geometrically that the area under the curve is the area of a semicircle, so it's 2 pi. We did it in a previous section, and therefore 1 over 4 times 2 pi equals pi over 2. So the average height is pi over 2. More or less 1.57. So it's pretty close to the top. 1.57 is not very far from 2, which is the maximum value. That's the average value of this function. Definition. The definite integral of the rate of change of a quantity capital F prime of x gives the net change or total change in that quantity in the interval ab. So here we have this idea that if you take the derivative and the integral, it's kind of cancelling out, so we still keep capital F, upper limit minus capital F of lower limit. So we have an integral of a derivative, it cancels out. Here's an example, and AP are very keen on these real-life examples. A chemical flows into a storage tank at a rate of 180 plus 3t liters per minute at time t in minutes. T is between 0 and 60. Find the amount of the chemical that flows into the tank during the first 20 minutes. So it's very difficult to understand these kind of word problems, but these keywords, rate, liters per minute, really need to make you understand that it's a rate, so it's a derivative. Liters per minute show us that when we're going to integrate this, we are going to find liters, and obviously liters is the amount that we want to find. Find the amount of the chemical. We want an answer in liters. So even without really understanding the question, just realizing that this is a derivative, we want to integrate that to find the amount, to find a result in liters. So the first 20 minutes means t is going from 0 to 20. We integrate this rate, 180 plus 3t, over the interval 0, 20. This is the integral. We plug in 20. We subtract the value when we plug in t equals 0, and the answer is 4,200 liters. Distance traveled. This is a question that is very easy. Consider the following problem. A train moves along a track at a steady rate of 75 kilometers per hour from 7 to 9 a.m. What is the total distance traveled by the train? Well, obviously, if it's a constant speed of 75 kilometers per hour for 2 hours, the train will travel 150 kilometers. If you actually sketch the graph, the velocity is constant, it's v equals 75. You notice that this answer 150 is actually the area under the curve. We have a rectangle with a base of 2, a height of 75, and if you do 2 times 75, it's really exactly what we did here. 2 times 75 equals 150. This shows how the integral of the velocity is going to be the position or the distance function. So when we integrate, the area under the curve, which is the integral, yields the position or the distance traveled between 2 points. So graphing the velocity versus time, we notice that 75 over times 2 is also the area of the rectangle between the line and the x-axis. That's really easy. What's amazing is that this idea of the area being the answer to find the distance traveled is true whatever the velocity is. So if the velocity was not constant, we can still keep this idea that the area under the velocity curve is going to give us the answer. If the velocity of the train varies, we can still find the distance traveled by finding the area between the curve and the x-axis. One short note here about terms that we have to be very aware of when we answer questions in quizzes, tests, or AP exams: a displacement and total distance. So here's a very obvious example that will point out this difference. A student walks from home to school 3 kilometers and then back home. His displacement is 0 kilometers. He was at home, he ends at home, displacement 0. But really, his total distance traveled is 6 kilometers. He did 3 kilometers and then he did 3 kilometers back. So that's an important difference that you need to memorize to answer questions. When a particle moves back and forth, see graph of velocity against time to the right, then the displacement will be given like that. If we have here the area A1, it's a positive number, the area A2 is a positive number, the area A3 is a positive number. If you want to find the displacement, you simply integrate. You don't have to worry about anything because the movement to the left is automatically subtracted, because even though the area is positive, the integral is negative. So you don't have to worry about anything. You can just integrate from A to B and it'll give you the displacement. The real problem is when you are asked to find the total distance. Here our particle was going to the right, and then for a while it was going to the left until here, and then it's going to the right again. So in this case you need to integrate each of these parts separately to add the positive values. So you'll have the positive A1 plus positive A2 plus positive A3. So the total distance traveled on AB, each part needs to be integrated separately, and then you add the positive values. Here's an example. A particle is moving along a line so that its velocity is given by the function v of t is t cubed minus 10t squared plus 29t minus 20 meters per second at time t. what is the displacement of the particle on the time interval 1, 5? Maybe we just want to look at what the particle actually does. The particle starts with a velocity of 0, so it's not moving. It starts to go to the right, it goes really fast towards the right, and then it continues to go towards the right, but slower and slower, until it stops. And then for a brief amount of time between t equals 4 and t equals 5, it's actually coming back to the left. And at t equals 5, it's stopped again. So the displacement is simply the integral of the velocity function between 1 and 5. Let's do it with a calculator. If you forgot how to do it, and you have a TI-84, you type in your velocity function with x, of course, not with t, and then you press second calc. It's option number 7, and you put in your lower and upper limits. It'll give you the displacement 10.667. However, if we want to answer question B, what is the total distance traveled, then we have to find the total distance traveled between 1 and 4, and then we'll have to add the area between 4 and 5, a positive value, because it traveled, even though it traveled back, it's extra distance. So between 1 and 4, we're integrating v of t, and then you can do it in different way. Here I just decided to change the sign before integrating, so it's minus the integral from 4 to 5. You can do all of that separately and put the positive values together in the end. You'll find that it actually went 11.25 meters to the right, and then it backtracked for 0.58 meters. So in total, it traveled for 11.83 meters. So this is the end of the second part. With that, you can do all of the exercises that are actually listed at the back of the notes. I'll have to add 2 more exercises to that list, but I'll get to that in the third part of the note, which is actually going back to the beginning of 5.4. Thank you.